So my project is on black holes, and the purpose of this project is to erase the mystery of black holes. So hopefully by the end of this presentation, you will all have a good understanding of exactly what black holes are and why they're so cool. So to begin with, since I'll be connecting black holes to the general theory of relativity a lot, I'm going to briefly explain what it is. So Albert Einstein stated that space and time were woven together to create this four-dimensional continuum called space-time. Now you can think of space-time as kind of like the surface of a trampoline, where when you place something really, really heavy on it, the fabric will wrap around that object. Large and massive objects cause a distortion to space-time. As you can see in this picture, Earth causes space-time to curve, like this. This theory also stated that gravity is a feature of space-time rather than a force. So we know that really large objects have stronger gravitational fields. Well, according to the general theory of relativity, gravity is a curvature of space-time caused by massive objects. According to this theory, the moon travels along the space-time curvature of the Earth, and the Earth travels along the space-time curvature of the Sun, as you can see in this picture over here. Okay, so I also have to discuss time dilation. And time dilation is this idea that time passes by at different rates depending on where you are in a universe and depending on the gravitational field of whatever you're near. So if you're near an object with a stronger gravitational field than the sun or than the Earth, then time will pass by slower. So if we were to place a clock on the Earth and a clock on the sun would go by a little bit slower just because the gravitational field of the sun is stronger than the gravitational field of the Earth. Okay, now let's talk about black holes. Black holes are regions of space, regions in space with very strong gravitational fields. A black hole has a photon sphere, an event horizon, and a singularity right at the center over here. Okay, so before I start talking about the photon sphere, I'm going to connect black holes to the general theory of relativity and space-time. So black holes cause space-time to curve so much because of their gravitational fields that they create a hole in space itself. And this is kind of better understood if we look at this picture over here. Now we saw how Earth caused space-time to curve like this, right? Because of its mass. That's Earth. Well, a black hole causes space-time to curve a little bit differently. As you can see, there's not really a point of return. There's not a curve, right? Everything's just kind of sinking down to this point. And that's because the singularity is it has an infinite gravitational pull. And we'll talk about this a little bit more when we get to the singularity portion of this presentation, but that's integral to understanding this idea that a black hole causes a hole in space because, you know, Earth has a gravitational pull and it can be calculated, right? But the gravitational pull of a black hole is so strong that it's just infinite, right? Nothing can escape it, not even light can escape it. So it creates a hole in space-time, which is very cool. Now, we also talked about time passing by very slowly near objects with very strong gravitational fields. Well, we know that black holes have infinite gravitational fields at their singularity. So, what would happen to time? Time would stop. So if we threw a clock into a black hole, then it would go slower and slower and slower until eventually it just stopped. So time does not pass in black holes, which makes sense, right? Because they create a hole in space-time, so there's no space and there's no time. Okay, now let's talk about the photon sphere. This is my favorite part. So the photon sphere is an area just outside a black hole's event horizon where the gravitational field is just strong enough that photons, particles of light, begin orbiting the black hole. So this means that if we were facing a black hole and you were standing at the photon sphere and you look to the side, light from the back of your head would orbit the black hole, so it would travel like this photon is right over here. It would travel all around the black hole and it would reach your eyes, which means you would be able to see the back of your head, which is pretty cool. Okay, now we've passed the photon sphere. Let's talk about the event horizon. The event horizon is a point of no return for black holes. The escape velocity of the event horizon exceeds the speed of light, which is the fastest thing in the universe. So like I said earlier, nothing can escape black holes, not even light. So if we were to watch somebody fall into a black hole, once they hit the event horizon, to us, they would just freeze. The image of them would just freeze, and it would slowly disappear. The person, on the other hand, would just keep falling into the black hole. But since nothing can escape the event horizon, not even the image of them falling in, we would never see them falling in. Event horizons can be anywhere from 5 kilometers wide to the size of our solar system. The radius of the event horizon is also known as the Schwarzschild radius. And the Schwarzschild radius is the radius that an object needs to be compressed into for the density to be so much that the object would become a black hole. This means that theoretically anything could become a black hole. People, tables, chairs, cars, anything. The Schwarzschild radius of the Earth is about the size of a peanut, which is 9 millimeters. So if we compressed all of the Earth into the size of a peanut, it would become so dense that it would become a black hole. This is really unlikely to happen, but for stars that have Schwarzschild radiuses much, much, much larger than 9 millimeters, larger than even the size of our solar system, it's more likely for their mass to become compacted into those areas. Okay, now let's discuss the singularity. The singularity is a one-dimensional point which contains an infinite density and an infinite gravitational pull. Now, people usually confuse this with the idea that, black holes are infinitely massive, but that is not true. They have an infinite gravitational pull. And gravity is usually associated with, the size of things. The sun is bigger, so it has a larger gravitational pull. But you can actually calculate the mass of black holes. It's their gravity that's infinite, and it's right here at this point over here called the singularity. Now, since there's infinite density and there's an infinite gravitational pull, then the laws of physics do not exist. Physicists say they do not exist because the math just gets way too complicated with infinite density and infinite gravitational pull. Okay, now let's discuss some theories. Now, I wouldn't go as far as to call this first one a theory. It's more of what would happen to somebody if they fell into a black hole, according to everything I've discussed in my presentation so far. So if a person were to fall into a black hole, they would pass the event horizon and they would approach the singularity. Because the gravitational field is so strong at the singularity, this person would be pulled apart atom by atom. If they went feet first, because of the difference in acceleration, their feet, these don't really look like feet, but their feet would be pulled apart first, and their body would start looking like spaghetti. This is spaghetti, if you didn't know. And that's why it's called spaghettification. It's a real physics term. Okay, now let's talk about our second theory. We're going to talk about wormholes and white holes. These are also called Einstein-Rosenberg bridges because Albert Einstein theorized them. Wormholes are basically like portals. This is a wormhole right here. Portals to a different universe. And for them to exist, there would have to be no singularity in a black hole. Instead, matter would be spit out into a universe that looked very similar to ours. In this parallel universe, time would go backwards. Matter would enter this alternate universe through a white hole, which is right here. And white holes are basically the opposite of black holes. They spit out matter, and nothing can enter a white hole. Unfortunately, there would be no way for humans to survive this journey to an alternate universe, and it would also take a very, very long time, much longer than the lifespan of a human. So hopefully now you have a clear idea of what black holes are and why they're so cool. Yeah, and thank you for watching.